Hello, welcome. In this video, we'll learn about the types of activity relationships. And that will be based on the previous lesson, which we learned about construction schedules, how to represent the network, how to sequence the activities, and how to perform critical path method calculations. So please watch the previous lesson to be able to watch this lesson here. So we will cover or explain that there is more into how to sequence an activity. So previously we're just representing this simple logic that A precedes B or B depends on A. So it's a simple relationship, but simple relationships are good. They're actually help us to develop easy to follow, easy to read schedules. But the problem is they are not really representing reality, and on field things happen in a different way than this simple representation here. And also simple representation results in longer schedules, and this is why on site it happens differently a little. So as an example here, why simple relationships result in longer durations is if I have this pipeline project, so the activities that need to be done, you have to dig the trench, you have to lay down the pipe, connect the pipe segments, and then you have to backfill. But the question here is, do you have to wait until you excavate the whole length of the pipeline, which is miles after miles after miles, until you wait until all of this excavation is done to be able to start laying down the pipes? And if you think about it, this is a lot of waste, right? Waste can be time. It doesn't have to always be material. So wasting time by waiting all of that excavated trench till the end of it to be able to start laying down pipes from the beginning. So you can see here the point that this simple relationship will result in long durations. And there are many ways around it. Still, you can use the simple relationship here, but you'll have to break down the activity, for example, into multiple activities. Maybe instead of just one activity as trenching for the whole pipeline project, you might divide it into stations or segments of the project. And you start now doing that simple relationship. Whenever I finish a segment, I will lay down the pipe, or whenever I trench, I will lay down the pipe in different segments, and you can phase it or sequence it this way. So it will allow for concurrent execution of activities. And we'll learn about completely different method than CPM, which is called linear scheduling. So that's a different lesson. So in order to go away from the simple relationship representation, A depends on B or B follows A, we need to have a little different representation of the activity here. So yes, we represent the activity as a node. So we don't say activity A depends on whatever previous activity or preceding. But now in this node, I will look at its start edge and end edge or finish edge separately. These are two important points of time. I don't have to represent the activity as this whole time period during its duration. It is an important event when to start an activity that can result in different things in a project. And also when I finish the activity, that can result in different logic, different things that can come after that, or maybe that finish depends on conditions or other activities to be done before you finish this activity. So now I will represent the logic of activities, especially not the whole schedule, but the activities that I want to represent it in a more realistic way, and I have more shortened duration of the schedule at that part of the project. So instead of saying activity A depends on, I will say start of activity A depends on, or the finish of activity A depends on. So that will result into kind of different combinations now. Instead of A depends on B, now I'm looking at A as a start and finish and B as a start and finish. You get the point. There are different combinations. There are actually 4 possible combinations of activity relationship types. So the first one is the finish to start, which actually is the simple relationship that we used so far in the previous lesson. So A depends on B. It's kind of, I'm implying that or in this case, sorry, B depends on A. I'm implying that the start of B depends on finishing A first. So that's the simple relation we have seen before. The other possible combination or type of relationship is start to start. So to start activity B, I have to start activity A. But there is no relation between whatever happened over the duration of A and B. There is another possibility, which is finish to finish. So to finish B, I have to finish A first. B and A can start at different times. They have different logic for starting, but for finishing, they are related or tied together. And then the last here is start to finish. So I have to start A to be able to finish B. Now in the next slides, we'll see different examples of these, but finish to start is the simple relationship we have seen before, so we'll not cover it. We will cover the start to start and finish to finish together because they usually use together to represent a sequence logic, a specific sequence here, which is concurrent sequencing. And then we'll see the cases for start to finish. So we'll start with the start to finish, SF relationship. So start to finish is the rarest relationship type to use in schedules. And this is not in only construction management practices, but generally any project management. When you have schedules, it's very rare to see start to finish relationship. From what I have seen, the main use case for start to finish is the case where you have a transition between a temporary system to a permanent system. So as an example here, let's say activity A represents the operation of a permanent power plant or permanent power generation system. And activity B is the operation of a temporary power generation system. So like you brought a generator on site and you're running it until you have the main power is online. So the logic here is you cannot turn off or finish the temporary power system B until you start and you have the permanent power system operational and you can start it. So that's kind of the only use case that I kind of found. Another use case which is following the same theme, like dewatering systems. So when you excavate deep excavation and you wanna like your current dewatering system brings the water or the groundwater down to a specific level, and you wanna lower or excavate more. So this means you have to lower the groundwater more. So you have to install another dewatering system. In this case, you cannot turn off the first dewatering system until you start operating the second dewatering system that will keep the groundwater down. Otherwise, you will have the excavation pit, drowned with water. You will be drowned in groundwater. So it's a very rare case to use start to finish. Concurrent sequencing, which happens when you use both start to start and finish to finish. So it's like twins. They come together to represent that concurrent sequencing. As an example of that is the pipeline project that I presented before. So trenching can start, and then you can have some lag or buffer between the spot where you finish trenching it and start, laying the pipe at this spot. Let's say a mile. So this buffer, by the way, can be duration, but it also can represent space. So I want to have a mile buffer between trenching and pipe laying. So that's one example here. And of course, at the last mile, you can actually work very concurrently in the same day. While you're trenching, the pipe laying can just follow it back to back like that. The other example is in concrete. So you start forming, so you put the formwork in place, but you don't have to wait until the whole roof is being formed to be able to put the rebar in. So you can have some sequence, like parallel sequencing here, or concurrent, by saying I will start forming, but then after a day or two, I will ask the rebar crew, the reinforcement crew, to come and put the reinforcement in the forms that are finished, or the parts of the roof formwork that were finished. So these are two examples. There's so many examples you can do. Whatever example that includes concurrent sequencing, you need to start something, one activity, and there is a second activity dependent on it, and you don't want to wait until the first one's to be finished. That's a concurrent sequencing. So there are many examples you can come up that you can use start to start and finish to finish together. So we have to be careful when using concurrent sequencing by applying the start to start and finish to finish relationships. They will mess up your CPM calculations. I use here more kind of a more professional wording here, interesting CPM calculations. But they really will make the CPM calculations don't make any sense. So we have to be careful not to overuse start to start and finish to finish. So let's show that by using this example here. So I have activity A and B. Activity B depends on A from both sides, the start side and the finish side. So to start B, I have to wait until A starts, and I wait also 1 day after that, so it's start to start relationship. And the finish of B here also depends on the finish of A, but there is no lag there. And this is just a zoom into a bigger schedule, but A here depends on some other preceding activities. So the early finish of the immediately preceding activities here, they finish at 20 days. So kind of when I start A, I will start at day 20 or time 20. So we'll do the CPM calculations for this part of the schedule, considering the two scenarios or two cases. When A is equal to 7 days and B is equal to 10 days, that's one case. The other case is flipping the durations. So let's see what's really happening here. So if A starts at 20, so it will start 20 with 7 days, you'll have early finish of 27. You have a start to start relationship with B with 1 day lag. So the start of A, early start of B will be 21. B is 10 days, so that means that B will finish 31. But wait a minute, I have a finish to finish relationship between A and B. So B can't finish until A is finished, which is the case, right? A has a shorter duration than B, so A will finish earlier, then B will have this time to finish, which is fine. So here the finish of B is basically dependent on that 10 days, that B needs 10 days to finish. It's not dependent on anymore on the finish of A, although I have still to respect that. The second case, I will flip now the durations of A and B. So now I start A at 20, because that's coming from the forward pass calculations from the activities before. And then at 10 days, so that will be early finish of A will be 30. I have 1 day lag between the start of A and B, so early start of B will be 21. Then B has 7 days duration, so I'll finish 20, theoretically 28. 21 plus 7, 28. But again, wait a minute, I have a finish to finish relationship, so B cannot finish until A is finished, which means that the early finish of B should be 30, not 28. So what happens here? Like I need only 7 days, but I ended here with a difference between early start 21 and early finish 30, 9 days. So I have kind of 2 days extra, so that there's something wrong here. But if you think about it, A will be able to start as early as 21 days. It only needs 7 days of work, but it's given 9 days because it has to wait anyway until A is finished. So that's the early time or earliest times to do the start and finish of B. So I can do this different ways on site. I can, let's say, split B into 2 activities. I can work for 3 days, have a break for 2 days, and then continue for 4 days. Or I don't have to stick to the early finish of 21 days. I can actually wait until the 23rd and then start B continuously, The crew will come, finish the work for 7 days, and then leave. And that's typically what's being done. But in this case here, you're actually pushing yourself or squeezing yourself and sacrificing the 2 days float that you had before. So that's kind of a balance. Do you start and keep the continuity of the crew, start late and keep the continuity of the crew, or you start early, have some slack in the middle or float in the middle, and then continue be after that. So that's a side decision to be made. But again, have to be careful when using concurrent sequencing. When you start and finish to finish together, expect that CPM calculations will be done a little different than what we have seen in the simple sequencing logic case. So that's the end of this video. And in the lecture, we'll see examples. So we'll experiment with the CPM calculations and such complex type of relationships, and a larger kind of full example of schedule. So I will see you there. Thanks for watching, and take care of yourself and those around you.